Okay, so this is it. Hello, I want to welcome you to my channel, YouTube channel, and I'm starting a series of videos in which I want to talk a little bit about neural networks, math stuff, engineering stuff, and I want you to be my partner in this journey. Okay, so I am going to talk a little bit about optimization, neural networks. In the future, I want to talk to change the subject of our videos to talk a little bit about numerical methods and finite element methods. So, in this series, we're going to talk a little bit about neural networks. And let me just introduce you to myself. So, my name is Ricardo Mafra. I am a mechanical engineering student. In 2024, I'm studying mechanical engineering in the University of Brasilia, Brazil. And I am in this journey, in this mission to understand and implement a neural network. Okay, so my goal here is to show the mathematical theoretics background in which the neural networks are based. And also, I want to make some Python implementations so then we can learn in the practice. And and that's it. So let's begin our video. Today, I want to talk with you about optimization. And let me just take this video right here, make it little small. Okay, so here it is. I want to talk a little bit about optimization, and I want to propose here an example. This is the XY plane. Okay, imagine that we have a function f which shape is this one. Oh, I have to stop doing straight lines. So imagine this function f right here. Okay, f, oh my god, f of x. Okay, perfect. Here, as you can see, we can we can observe two minimum points. Okay, and in neural networks, our goal is to minimize a function called the the learning function. Okay, so a neural network is basically a math function that you want to minimize, and by minimize, we are we know that if we minimize this function, we are getting the best, the most optimized answer for our problem. Okay, and so that's it. We have in this case two minimum points. This one is the local minimum and this one is the global minimum. And how do we do to find these points? By hand, we can evaluate the gradient of the function f and make it go to 0. So we want to find the points where the function gradient of f is 0. And here we are going to find these 2 points here, doing it by hand, evaluating everything. We're going to see that these 2 points are the minimum. But we do not want to do this manually. We want to do it by numerically, with our computers. So how do I do this with our computer, with my computer? I want a method to find to find the roots of a function. So this is where we are beginning to understand neural networks, okay? Yes, that's it. This is what I want. My video along with the Taylor series. So how we are going to find, not by hand but by with our computers, how we are going to find the roots, the points where the function equals 0 of a function f. So to do this we use the Taylor series. The Taylor series says that we can approximate a function as a function of its surrounding neighbors points. So here is the Taylor series mathematically formulated, and here we are expanding it for us to see the summation here. So we are approximating the function f by its neighbors points, x, k, for example. So here we are using the first derivative of the function f, the second derivative, and so on, the third, the fourth, the fifth. But I had proposed a logical quote here. Imagine that xk is very near the point x. So the subtraction power to a number n is going to be very near 0 for every one of the n's that are greater than 1. With this conclusion, we can just forget this second, third, fourth order terms, and we have this function here. Okay. So we started from the Taylor series, and now we have this function, knowing that xk is very near the point x, the point that we want to approximate. And consider that x star is the root of the function, is the point where the function f becomes 0. So I'm just putting x star here. We know that f of x star is 0, and now I'm just isolating the point x star in one side. And then I have this equation. This equation right here is the Newton's method. And we can use it as an iterative way to find the point xk in which the function f becomes 0. So what we are doing right here, we are updating the value xk by doing a subtraction with this term right here. The function f evaluated in the point xk divided by the first derivative, the function first derivative evaluated in the point xk. So we are updating the value, the first estimate value that we have. Well, what is it? What are we doing? This method proposes that we are starting from a point right here. This point is the point xk, okay, and we want to find this point here. In this first method, we are not going to find the minimum value. We're going to find the roots, the values where the function f equals 0. But we are going to see later on how do we do to find the minimum, okay? So we start from this point xk and we are updating it by making that subtraction. What is that? What is this term? f of x divided by the first derivative of x. We can write it as the following sentence. So we are getting the value of the function in the point xk and dividing it by the first derivative term. And we make this subtraction right here. Let's see how this method works in the real life, okay? So imagine that we have this function here, and I'm going to show this function to you. So this is the function 3x squared minus 2x minus 3. This is the function. There we want to find these 2 points here. The points where the function f equals 0. So what I just did in this piece of code here, I declared the function f, the first derivative of f, and then the Newton's method. So here here is the first derivative of f, the function f, the Newton method. Here is the heart of the method. Okay, so we are updating our first estimate by doing this subtraction. Okay, let's see how it works. Just look, in 4 iterations, the method found the root of the function f. And this answer is a function can change if we use initial estimate, a different initial estimate. So here I use the -2 point. Look, I started here, the point x equals minus 2, and then I was getting down here in this function and found this point here. But this answer can change if we use a different starting point. And look, the method found a great estimative. Here we can compare with our visualization. We can see if the answer is right. So minus 0.72, minus 0.72, right here, minus 0.72. It's at least visualization looks right. Okay, so let's use a different starting point. We are starting now in the point xk equals 2. Okay, look, the method found a different answer. This answer is the other root point. And here I printed out the answers. So the method found these 2 points, and now we can see that it's correct. Okay, so but optimization in optimization we do not want to find the zeros of the function f. What is the difference between optimization and this method of finding the roots? We are going to see. But we know also that in neural networks we have n-dimensional functions. A neural network, a function can have n-dimensional inputs. The x can be a vector, and so on. The things get big, real big. And I want to show you what is the difference between one-dimensional Newton's method and an n-dimensional Newton's method. Imagine that x is a vector and f is a multidimensional function. Therefore, the Newton's method becomes this one. It's the same thing. We are updating our first estimate by doing a subtraction of this function, of this product right here. And what is this J right here? This J is the Jacobian matrix evaluated at the point xk. Jacobian matrix evaluates the gradient of the function f. Okay, and this now becomes a vector function, a vector method. So that's why a matrix appears right here. Okay, what is the difference between minimization and optimization? It's quite simple. Minimization, we want to find the roots of the function f. In optimization, we want to find the roots, the values of x, where the function f equals 0. We want to find the roots of the gradient of f. It's the same thing, but different functions. So we are going to use the Newton's method as we did previously. And the Newton's method for optimization is the same. We are updating the first estimate that we had by doing a subtraction. And now the function is no longer f, but is gradient of f. And here the matrix is no longer the Jacobian matrix, but is the Hessian matrix. The Hessian matrix is the gradient, is the Jacobian matrix of the gradient of f. It's the same thing. We can see it as the second derivative of the function f in respect to all of its input values. Okay, I'm not going to show the matrix as I did previously right here, because it's not our goal. Okay, so imagine that we have this function right here, third order function. I'm going to plot the function here for you. This is the function that we have, and we want to find the minimum point, this minimum point here. And for you that maybe are already quite familiar with math and calculus, we know that this point here and this point here, the gradient of f equals 0. So this method, we have to take care, we have to pay attention in the point where we are starting the method. If we start right here, the method is going to find this point here, but this is not the minimum of the function. If we start here, the method is going to find our minimum. So let's see. By hand, we can do it, and find the gradient of f. We can find that the point 8, that this point here is the minimum. 8 divided by 3. This point here is the minimum of the function. We can achieve this result by hand, but we do not want to find the answers by our hands. We want to find it with our computer. So here I did the same thing. I have declared the functions, the Hessian, the gradient of f in the Newton's method. The same thing I did. I declared the function, the gradient, the Hessian, and the method for us just to numerically find these values. Okay. So starting from the point xk equals 2.0, let's see where is it. Starting from here. Okay. We found that the minimum of the function is the point 2.67. And this is what visually you can see here. 2.67 is the minimum point. Okay. And look that this method is very quick to find the answer. In only 4 iterations, the method found it. And something that I want you to pay attention to, keep in mind that in every iteration, the Hessian, the 1 divided by Hessian, was a different value. So it was changing in every iteration. The value changed. In the next videos, we are going to study a little bit about gradient descent methods and stochastic gradient descent, and we we are going to see that these methods are almost the same, but here instead of using the Hessian matrix, we are going to use a number, a floating point number. We're going to use a scalar value in which will not change every iteration. It's going to be the same. But here we can see that we are going to see that the gradient descent method is no longer so quick as the Newton's method to find the answer. Okay, so here we found, starting from the point xk equals 0.5, we could find another point where the function gradient of f equals 0. That is the point 0. We can see here 0 is the point where the gradient equals 0. But we know that this is not the minimum of the function, just for you to see the difference. And I want you to see a different example. We are considering now a vector function with x, y as inputs. And here I did manually the evaluation of the Hessian for us to implement. And now I'm going to show how this function looks. Okay, this is the function that we are considering now. This is a convex function. We are sure that this point right here in the middle is the minimum point of the function. And I wanted you to see these curves right here, in which we can make we can look and we can make a good study of these curves in order to see what the method is doing. So these curves right here in the xy plane are the level sets of the function f. What are the level sets? Level sets are the curves in which the function f equals a constant number. This is the level sets. And how do we help us in the study of optimization? It helps us because we know that the gradient of f is pointing perpendicular to these curves right here. Look, the gradient of f points towards the direction of the f, which is the growing direction. So now we can see that the growing direction is this one, from the blue curves to the red ones. This is the direction in which the function f grows. But I want you to look to something very important in this point, okay? When we are finding the minimum value of the function, I'm going to show you here in the code. And if we are willing to find the minimum value, now you know that we have, now here is not the function f, but the gradient of f in the Newton's method, and here is the Hessian. What are we doing? We are starting from an initial point called xk, and we are updating it, making this subtraction. This we already know. But the thing to look here is that in every iteration we are walking in the opposite direction of the gradient. It's very important. We are not making the update as we want. It's not in the direction we want. It's not so simple. We are doing the update of our first estimate in a certain direction, which is the opposite direction of the gradient of the function f. And this is very, very important, because look this image right here. The gradient of the function f points from the blue curves to the red ones. So it's points in the direction in which the function f grows. But for the update of our first estimate, we are walking in the opposite direction of the gradient of f, from the red curves to the blue ones. This is what we are doing in every iteration. And the Hessian, this value that changes right here, as we saw, the Hessian is the amount that we are going in that direction, is the intensity in which we are going in that direction. Okay, so let's see in practice, let's implement this code first to see if the method finds the right answer. So here I did the same again. I was declaring the functions. I implemented the gradient of f, the Hessian. Now it's a matrix because it's a two-dimensional function, and the Newton's method. So I started from the point 4 and 7. Let's see how it looks like. So here, in just 2 iterations, the Newton's method found the right point, the point 0, 0. And this answer was so quick because this function is a convex function. Imagine that we are riding our bikes in a very, 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 very steep descent. Imagine that you are walking, we are riding your bike in your skate in a very, very great slope road, and we are going down. So you go down very quick because the slope of the function is very, 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 very big. Here you can see that the Newton's method is going downhill until the method find this point right here. So this is what the method does. What I want you to keep in mind is that the Newton's method walks in the opposite direction of the function of the gradient of the function f, and in every iteration the methods goes in that direction, and the intensity in which the method goes in that direction is determined by the Hessian value. Okay. And what are the difficulties of the method of Newton's? Is the second derivatives evaluation. When we have multidimensional functions with multidimensional inputs, the evaluation of the second derivatives are very, very hard, and we avoid doing these calculations. We want to be we want to have something that we will not have problems, and we do not use the Newton's method in neural networks applications. And in the next video we're going to talk a little about these other methods of optimization. Very, very, very old method, but it's the mostly used method in deep learning applications. And that's it. So I hope that you enjoyed this video. I hope that this video helped you in something in your life, and I want you to be my partner in the journey, and see you there in the next video.